Hi everyone, thank you for checking out our senior project webpage.
We are the Inverted Fluorescent Microscope team, otherwise known as Team Team.
Our project was brought to Cal Poly's Mechanical Engineering Department by Professors Hans Mayer and Benjamin Hawkins, directors of the Microfabrication Laboratory here on campus.
They sponsored our project because the Microfabrication Laboratory was lacking an essential research tool, an inverted fluorescence microscope, or IFM.
Fluorescence imaging is a very effective way to observe microfluidic systems, but commercially available tools are cost prohibitive.
We were tasked with building an inverted fluorescent microscope using components already owned by Cal Poly to reduce the cost. This microscope is intended to be a flexible platform for future instruction and student research.
We began our design process by defining our sponsor's request in engineering terms. Once we understood the problem and science behind IFMs, we began to investigate potential solutions. The design of our IFM was divided into three subsystems: optics, mechanical stage components, and controls, integrated into one final system. We observed that there was little interdependence between the subsystems, so decision matrices were used to select the best options for each area. Throughout the design process, we just interacted with our sponsors and peers through design reviews and made adjustments to our design based on their feedback. Due to the COVID-19 pandemic, Cal Poly made the transition to online learning for the entire spring quarter. This meant that we needed to adapt our build strategy to work remotely. Working with Dr. Mayer, we completed our assembly online using Zoom to communicate live. Here is our verification prototype that currently sits in the metrology room within Cal Poly Microfabrication Lab. We are able to complete almost all the assembly. The only portions that we could not finish were restricted by an inability to purchase components.
The microscope is capable of both bright field and fluorescence microscopy, involving the use of two light sources and two optical paths. Standard bright field microscopy is used to locate the sample and bring it into a sharp focus. The microscope can then be switched to fluorescent mode to analyze specific sample features in greater detail by tagging these features with a fluorescent dye. Bright field mode utilizes a broadband fiber optic illuminator, which is focused onto the sample with a lens attachment. The light passes through the objective lens, emerging collimated in the infinity region. This infinity correction helps to eliminate design constraints by making the distances between optics components after the objective lens non-critical. Light is redirected once by a 45-degree mirror, again by a 50-50 beam splitter, and transmitted through the tube lens to the camera. Fluorescence illumination is accomplished by a single wavelength LED that shines light through the beam splitter, is redirected by the plane mirror, and passed up through the objective to the sample. The incident light excites a fluorescent dye within the sample, which loses energy and emits fluorescence at a longer wavelength. The fluoresced light travels back through the beam splitter and is selectively transmitted by a corresponding filter to the camera. Optical components were selected on the basis of compatibility with our chosen objective lens, with regard to design constraints based on the other mechanical and electrical components, as well as project budget.
We were able to find a used industrial XY stage online, and were fortunate enough to have two 2-inch linear actuators available to us in the clean room. Since these actuators only push in one direction, we designed a spring system to return the stage. These springs were selected to reach our 2-inch travel requirement while minimizing load on the system. We made sure that the springs had enough starting force to preload each axis, but a low enough spring constant not to overload the actuators. We fabricated mounting brackets to connect this actuation system to the stage. The best way to keep our microscope flexible was to utilize rapid prototyping for these components. This had the dual benefit of facilitating iteration and reducing cost. We anticipated that PLA would be an appropriate material because the springs we selected only generated forces up to 20 pounds. Since PLA is a brittle material and 3D printing can lead to inconsistent material properties, we had to confirm that our brackets were safe. We designed a load test to verify that they could withstand at least twice their service load. All the brackets tested passed, but anywhere we saw deflection, we added material to the part.
The maneuverability of the stage is handled by two actuators controlled by Arduino microcontroller. Both actuators have two encoder channels which are used to determine the distance traveled by the actuators. The actuator speeds are directly proportional to the actuator encoder counts to maintain extrusion speed as the spring forces increase. Because the spring forces are large, a DC power supply is attached to the system to raise the actuator operation voltage to 12 volts, so full actuator extrusion is possible with the spring returns in place. Limit switches are also used to prevent the actuators from crashing during retraction and extrusion. On system startup, the user will be prompted to begin a zeroing function that retracts the actuators to the reverse limit switch to zero the encoder counts, then return to the zero indicator on the actuators. Afterwards, the control system moves to the joystick mode, allowing the user to move each actuator independently with each actuator corresponding to an axis on the Cartesian coordinate system. If the user wishes to use certain distant values instead, they can switch to the programmable path mode by clicking the button on the joystick. In the programmable path mode, the user interfaces with the Arduino stereo monitor to enter the encoder accounts as the target distance values for the actuators to move forward. In order to switch back to the joystick mode, the user must wait till the initial select actuator prompt is displayed.
By following the engineering design process from research and product conceptualization to manufacturing, assembly, and testing of our verification prototype, our team was able to deliver a low-cost modular device for future student research and instruction.
While there are certainly opportunities for additional design development and add-on capabilities, we are confident that our product will achieve its goal of expanding the use of bright field and fluorescence microscopy accessible to undergraduate students in the microfabrication laboratory.
Again, we are Team Team.
Thank you for watching.